G'day, I'm James. About every decade or so, a raging debate evolves about the issue, what is multiplication? Now, it seems like a strange thing to debate about, but people really want a concrete answer. What is multiplication? You know, people say it's repeated addition. Say, no, you can't have students think it's repeated addition all the time because it's not repeated addition. Then is it area? Maybe, maybe not. Is it scaling? Is it unit conversion? Is it something else? It's all over the place. And people will say, enough, tell me what actually is this thing called multiplication. It is very confusing, very subtle, and I think the debate, personally, is actually a little bit misguided. I think the word is wrong in this discussion. So I'm going to explain what I mean by that and what my answer to the question, what is multiplication, is. All right, but let's make sure we understand what's going on. Repeated addition. I mean, if I take something like, 3 times 4, in a very simple world of the counting numbers, we think of this as groups of. Multiplication is groups of. So there's 3 groups of 4. So that really is repeated addition. A group of 4 and a group of 4 and a group of 4, that would be 12. So 3 groups of 4 gives me the number 12. Okay, great. But then, you could say, well, it's really area, because if I take a rectangle that's, say, 3 meters by 4 meters, here goes a 3 meter by 4 meter rectangle, 3 meters by 4 meters, its area, could chop it up in all sorts of clever ways, would be 12 meters squared. But now things are a little bit subtle. You might say it's not a big deal, or maybe it is a big deal, because I've gone from just pure numbers here to numbers with units attached to them, 3 meters, 4 meters, and the answer is not in the same unit, it's now meters squared. It's got a different unit to it. It's kind of interesting. Scaling actually has the same sort of trouble. It's got like a lack of unit. For example, I could say 3 times 4 meters. What I mean by scaling there, we'll take a length of 4 meters and scale it up by a factor of 3. So I'm going to stretch it to 3 times as long, and I'll get something that's now 12 meters long. Oh, the number 12 meters squared, and now it's the number 12 meters. Actually, if you think of unit conversion, it gets kind of messy, like you can do a mixture of things. For example, there's 3 feet in a yard, so therefore 4 yards is 3 times 4 feet, which is 12 feet. So now I've got like a mixture of like yards and feet going on within the same equation. Getting very, very strange. And this is just sticking with whole numbers in different contexts, in like a pure mathematical context, in like a geometry context, in like a science context or something. It actually is a little subtle there. But what about other types of numbers? For example, fractions. If I just say half of 6 and say that's 3. I just used the word of there, which is a different notion again. Maybe multiplication is the word of. And I say, well, okay, I guess it is, but does that only work for the world of fractions, or can I use the word of in other contexts as well? In fact, let's do another strange context. Negative numbers. All right, so what's multiplication in the world of negative numbers? If I say something like 2 times negative 3. Well, maybe I'm still in my repeated addition thinking. If I go back to that, I say, well, this is like 2 groups of negative 3, so it's a negative 3 and it's a negative 3, so I get negative 6. Okay, I guess that was felt kind of random to go back to that one. Could I use the area model? No, you can't side x to negative 3. Can I scale? What's a length of negative 3 units long? Oh, a little weird. Actually, it gets weirder still. What if I did negative 2 times 3? Even the repeated addition model goes out the window there. Negative 2 groups of 3? That makes no sense. That makes no sense. And the worst one of all is actually negative 2 times negative 3. Negative 2 times negative 3? Negative 2 groups of negative 3? No idea what that means. Even though I know I've been trained to say positive 6. Plus 6. As a mathematician, I do say that, because I know there's going to be logical consequences to my answer to this question, which I want to reveal today. What's my answer to what is multiplication? It's not one that society is going to like, because society expects, demands even, that mathematics be concrete, real world, absolute, have definitive answers. I can't give a definitive answer. Look, even how we teach it in the curriculum, we go through all these different definitions of multiplication. We never say what multiplication is, we just bounce around to different manifestations of multiplication. Multiplication manifests itself in different ways. So maybe the word is there is just too absolute and it's actually at odds with what mathematicians do. What mathematicians do is they step away from that real world, practical, concrete scenario. Things need not be absolute. Things have nuance, things have context. That's a shocker to most people in society. But mathematicians will step away and say, what's really going on in all these different scenarios? What's the common structure I see? They look for structure. And once they found structure, they can see it manifest itself in different ways, in different scenarios. Which then brings us back to practical real-world application for those different scenarios. So mathematicians do attend to real-world practical scenarios by stepping away from them, looking at a bigger picture, and then they can apply them in different contexts in one fell swoop. That's hard. That's not the impression we give of mathematics to the society as a whole. So what I want to do is actually go through that story about having a step back from structure through the story of numbers and answer this question, at least my personal answer of what multiplication is, well, how to handle this question. So what I want to do now is going to be a bit strange. I want to give an overview of the history of numbers in a very strange, weird, wacky way through the story of solving equations. But then you'll see what's really going on. So here goes. Let me clean the board. Back in just a moment. Okay, so what's the first mathematical activity humankind ever probably took part in? Well, it's probably counting. We humans counted things very early on. So we probably invented the counting numbers 1, 2, 3, 4, 5, 6, and so on very, very early on in our mathematics. There's evidence that cavemen from 30,000 years ago were counting things on tally sticks, on bones of wolves and so forth. So counting was definitely a natural part to our human experience. And in fact, I'm going to go as far as say this. I think the counting numbers and their arithmetic is the only number system we humans, individual human beings, truly understand and can internalize to some significant degree. Everything we do beyond the counting numbers is getting more and more abstract and therefore a little more foreign to us. We might have some intuition for it, but I think it's only the counting numbers we truly understand. Now, let me show you what I mean by that. I mean, for example, you can certainly have the counting numbers. You can count 5 deer or 5 dogs or something, but I'm going to count 5 dots. So here's 5 dots. 1, 2, 1, 2, 3. Oh, in fact, look what I just did. I did 2 dots and then I added 3 dots and it's just discovered addition. Put 2 dots and 3 dots together and I see I've got 5 dots. So actually right there I can actually play with a mathematical operation which I'm going to call addition. What's lovely about what I just did, because I did 2 dots and then 3 dots. I looked this way, saw 2 dots and then added 3 dots. But if I look this way, I can see 3 dots plus 2 dots, 3 dots plus 2 dots. And without even saying the number 5, I know the answer has to be the same. It has to be 5. Philosophically, it just has to be 5. Had 104 dots followed by 107 dots. Whatever that answer is has to be the same as 107 dots followed by 104 dots. So I can see some structure right now in the mathematics of the counting numbers that feels intuitively real to me. I feel like I really own this. That any counting number plus another one, A plus B, look at it left to right, you'll get the same answer if you look at it right to left, but it's just the same picture viewed from 2 different directions. All right, so you see I found some structure already to addition. Another structure could be is like if I had, say, 2 dots, here they are, and I add to them no more dots, add nothing more, I still got 2 dots. So some number plus no more dots is just going to be that same number of dots. So great, I can list all sorts of properties of this mathematics I've discovered, the counting numbers, that feel so right, so natural, so true. And then go a little bit further. I might invent something called, I don't know, multiplication. 4 times 5. And in this world, it really will be repeated addition. What I mean by that is 4 groups of 5. Here's one group of 5. Here's another group of 5. Here's another group of 5. Here's another group of 5. Okay, pretty random. That's 20 dots. I do admit that's 20 dots. But not very much structure there until I have the epiphany to think, oh, let's arrange our 4 groups of 5 in a very systematic way. Here's one group of 5. Here's a second group of 5. Here's a third group of 5. Here's a fourth group of 5. There is 4 groups of 5 who look this way. All right, 20 dots, grand, but here's the amazing thing. If I look this way instead, I see 5 groups of 4. It's the same picture, it's the same 20 dots. 5 groups of 4 happens to be the same as 4 groups of 5. Which is pretty amazing because this actually doesn't sound symmetrical. 4 groups of 5 sounds very different from 5 groups of 4. But the amazing thing is 4 groups of 5 and 5 groups of 4 are actually just the same picture looked at from 2 different perspectives. Therefore, they must have the same answer. So I've just discovered a property about repeated addition. Doesn't matter if you do it 4 groups of 5 or 5 groups of 4, you'll get the same picture in the end, if you're systematic about your picture, of course. Beautiful. If I have, say, 3 groups of nothing, 3 groups of nothing equals nothing, nothing, and nothing, I have nothing. So I can write down a property like this. A times 0 is 0. Beautiful, beautiful. And if actually I can identify more structure, I can do a mixture of addition and multiplication together. For example, suppose I did 4 groups of 2 plus 3. So here's my 2 plus 3 picture, 2 plus 1, 2, 3, whoops, 3. Now I did 4 copies of that. One group of 2 plus 3, second group of 2 plus 3, third group of 2 plus 3, fourth group of 2 plus 3. There's 4 groups of 2 plus 3. But I could see this picture really has that chunk, 4 groups of 2, plus this chunk, 4 groups of 3. It's really 4 groups of 2 plus 4 groups of 3. So that gives me another rule about how multiplication and addition seem to play with each other. A times B plus C. A groups of B plus C is A groups of B plus A groups of C. Whoops, that's a little bit neater. Equals A groups of B plus A groups of C. And I can see it right there. I own that. I personally, my brain, my humble human brain, can actually internalize that and make sense of that. So there's the basic structure of the counting numbers, which makes perfectly good sense to me. I can understand that. That's grand. But we soon learned that counting numbers were not enough in mathematics and life. For example, if I'm doing this being a little more mathematical now, let me look at the history of numbers through equations, which is kind of an absurd way to give a history of mathematics story, but here goes. We have the counting numbers. I guess you also have the number 0. I guess I added 0 to my list. And this is great because I can solve mathematical equations like x plus 5 equals 8 has a solution in the system. X must be 3. 3 plus 5 is 8. But this system is not actually adequate for all types of equations. For example, try to solve x plus 4 equals 1, and there is no number that solves that. So we said, oh golly gee, to actually then solve all types of equations, we need new types of numbers. So people said, oh, let's invent the opposite of the counting numbers, the negative numbers, and add them to the list. -2, -4, 3, -4, -5, and so on. Grand, because now I can solve an equation like that. -3 plus 4 equals 1. And there's even practical application at the time for this, because people think of like profit and debt all the time. Equations like that, you know, I owe $4 and I've got $1 in my pocket. How much do I actually owe? Oh, how much do I have in my pocket? That sort of thing happens all the time. I've got temperatures going above the freezing mark, below the freezing mark. So it's actually practical application, which makes people think that mathematics should always be practical. Okay. But then things get a little bit weird because I'm not quite sure what happened to this list. Because I just invented a new type of numbers. Should I expect this to still be true? All right, but before I go to that issue, there's more types of numbers. Because people realize, okay, the negative numbers are great for things like, you know, x plus 10 equals 7 and so forth. They're also great for things like, you know, 2x equals 8. X equals 4 would work. 2 times 4 is 8. Or 2x equals -8 even. -4 would work. Grand. But an equation like 2x equals 11 can't be solved in the integers, these positive and negative counting numbers. So I tell people, oh, we need new types of numbers. Okay, clear type of numbers we're thinking about are fractions. So let's add to the number system all the fractions so we can solve more types of equations. And this is all grand. And even those have a practical application, because I often talk about I need half a loaf of bread or I need a third of a dozen eggs. So fractions have, you know, practical real world application. And again, I've let go of what all this means, because all this means is I just know is true for that top line. What's going on for the bottom ones? Don't know yet. I'm just inventing more and more numbers. Because I realized after a while, in fact, mathematicians realized this about the year 500 BC, around the time of Pythagoras, some equations can be solved in fractions. For example, x squared equals 9 is has nice solutions. In fact, x could be 3, or it could also be -3. But something like x squared equals 2, people realized, can't be solved in fractions. That is quite a shock in the history of humankind, that not all square roots can actually be fractions. So people said, oh, we need new types of numbers, so we start solving more and more equations. So people added to this list all the things they called irrational numbers, things that aren't the ratio of 2 integers. Grand. So now we can solve equations like this, solve that, we can solve that, we can solve 4x equals 7, all sorts of equations like that. Has the story ended? No. Because after a while people realized, well, this is all grand, but there's still equations we can't solve. X squared equals -1 has no solution in the system. So people said, oh, we need more numbers so we can actually solve these types of equations too. So people invented the complex numbers and added them to the list. But now it's getting worrisome, because it seems like we're going to keep discovering more and more different types of equations that can't be solved, and therefore need to keep inventing more and more and more and more and more types of numbers. Very abstract, just for the pure wonders of this, that we're playing this game, like how many numbers do we need to cover all of mathematics, yet alone what all this stuff means for these new numbers. All right, but then, first of all, a big thing happened in the 1800s, around the year 1800 in fact. I think it was Argan who was actually the first to give a concrete proof of the question. Does this story go on forever? Do we need more and more and more types of numbers, or will the story eventually end? And he proved what's now called the fundamental theorem of algebra, which says, actually, stop there. The story stops there. Once you've got the complex numbers, you don't need any more types of numbers to solve basic polynomial equations. This is it for all of algebra. You need nothing more, which is amazing, because the worry was you have to keep on going. So actually, this is all the types of numbers you need. Fundamental theorem of algebra says the story of the types of numbers you need stop at the complex, which is beautiful and amazing and abstract, and it's taken us way away from practical applications. All right, so now we're going to go back to, all right. So we keep inventing these numbers. I can see practical applications for the counting numbers, but I feel like I intuitively own those. Negative numbers I can see make sense for profit and debt. That sort of happens. Fractions starts making sense. Irrational numbers, maybe, like the diagonal of a square. Apparently a square root of 2 is irrational. Complex numbers? Okay, so what's the game going on here? Well, okay, turns out the amazing thing about mathematics, every system here actually does have practical application. Even electrical engineers realize that once you go to complex numbers, you've got all these sines and cosines in their work about sine waves and cosine waves, but if you write them in terms of complex numbers, all of that trigonometry stuff becomes ridiculously easy and life becomes really good by rephrasing all the trigonometry in terms of complex numbers. So even something abstract as this has practical application even to this day. Math always seems to deliver that way. But I want to go back to this question about, okay, these are innate and true for the counting numbers. How can I extend these rules through all these different systems? Which means I need a notion of addition, I need a notion of multiplication, and I'm not quite sure what these things are going to mean. All right, so the hard one is just even going from the counting numbers to the negative numbers. So let's play with that. So, all right. So 2 times 3. Okay, if I'm in the world of the counting numbers, which I am for 2 and 3, repeated addition is fine, because in that world I said that's what multiplication is. In counting number world, multiplication is repeated addition. There's 2 groups of 3, which is 3 plus 3 is 6. Now let's start getting a little bit strange. 2 groups of negative 3. All bets are now off. However, it seems compelling to still think repeated addition right there. Think of this as repeated, one group of negative 3 and another group of negative 3. 2 groups of negative 3, in which case that's negative 6. So now I'm playing. I've got no reason to believe that, but it just feels right to me from my intuition about counting numbers. This now is getting strange. Negative 2 groups of 3, I have no idea what that means. And I'm honest, I have no idea what that means. Now I know you're probably yelling at me right now, Tanton, James, just switch them around, make it 3 groups of negative 2, just use this property. Okay, so you're saying to me, what we know is true for the counting numbers, we feel should be true in this scenario as well. So the question is, can we extend this structure to make it all work for the negative numbers as well? In which case, if I'm going to play this game, I could say this is 3 times negative 2, 3 groups of negative 2, which is negative 6, and that's looking good. That's looking great. All right, so you just said to me, you want to step away from practical application. Let's just use this structure that feels good in one scenario for the counting numbers. Does it keep working? Good question. Well, gets a little bit worrisome for this one. Negative 2 groups of negative 3? No idea. Negative 3 groups of negative 2? No idea. Not helpful. Not helpful. So what should that be? Now, people really struggled with negative numbers throughout the history of mankind, of humankind, all the way through. They struggled all the way through. It wasn't until the 1800s, very late in the history of mathematics, the mathematicians actually did exactly this. They said, do you know what? We don't know what negative means. I know that Brahmagupta said it should be positive. He said he felt like the mathematics would be consistent. We said this is positive. Euler in the 1700s actually said that should be positive as well. He actually tried to explain it with profit and debt. But it wasn't until the 1800s that mathematicians really looked at these basic rules and said, do you know what? If we follow these rules and actually follow their logical consequences, we do actually get a system of mathematics that matches our intuitive sense of the counting numbers. Whoa! So actually there is an answer to this as a logical consequence of these rules. Here's the trouble. I have no idea what it means on a practical sense. The society wants me to give a practical application of that, a practical representation. To be honest, I can't. Now, there are very contrived examples out there. You can imagine like watching people walking forwards and backwards on trains on a movie as the movie's sped forward and sped backwards while the train's moving forward and backwards. You can do sorts of weird contrived things like that to get an answer why that should be positive 6. It's not natural. It really is contrived. The fact is, this is just a logical consequence of what the game we're choosing to believe. That what we feel is true for the counting numbers should be true in this context as well. We're trying to extend that intuitive feel. So how does these rules lead me to say that has to be positive 6? Well, I'll show you. It's positive. As follows, excuse me. All right. I use this one. We like to believe that anything times 0 is 0, in which case negative 2 times 0 should be 0. Woo! Okay. Now I write that 0 in a bit of a funny way. I write that as negative 2 times 3 plus negative 3. And that should still be 0. Negative 2 times 0 is 0. All right. Now you can see what I set myself up for. This one. Negative 2 times 3 plus negative 2 times negative 3 has to be, well, nothing's changed really on the left-hand side. It's still 0. Great. Oh, -2 times 3, that's the weird one. Think of this as 3 times -2 plus -2 times -3. Still 0. I haven't really done anything deep here. Oh, 3 times -2 is what I just did earlier, I believe. That's actually -6 plus, oh, -2 times -3 is the mysterious thing I was wondering about, but I know it has to be 0. -6 plus that must be 0. Logical consequence, no choice but to say that's +6. That's +6. All right, so these basic rules, these things that feel so right and true about the counting numbers, can be extended to the negative numbers in a very natural way, but there's going to be some weird, unintuitive, logical consequences. One of them is that negative times negative has to be positive. You can probably argue with it, probably help students get sort of an intuitive feel for it by creating models of people walking on number lines backwards and forwards, but actually that's not the real reason, and that's actually the mislead of mathematics. What we do as mathematicians right now is looked at the structure we like so much and saw its logical consequences, and it happens all over the place. For example, let's go from the next set of numbers, which is to fractions, in which case the word of, people say multiplication is of, and I actually agree with that, because in the world of fractions, the word of behaves just like this with respect to addition. For example, a half of a third. You can actually draw a little picture of this. We say, okay, in this world, a half of a third. So here's a third, here's a half of a third. Compare that to a third of a half. So I'm looking for this rule right now. Does that make sense in this world? Well, yes. Here's a half, and here's a third of a half. It's the same picture in the end. So actually you could argue that the word of is behaving this way in terms of multiplication in the fraction world. A half of 0 is nothing. That fits. A half of 4 and 6 would be a half of 4 and a half of 6. That makes sense. So actually, what's going on here? The word of follows this behavior precisely in the world of fractions. Therefore, multiplication has manifested itself with the word of. Of does deserve to be called multiplication in fraction world. Whoa. In geometry world, if I'm doing some scaling of lengths, you can imagine this. 4 meters and 3 meters, double everything, I'll get 8 meters and 6 meters. You can see this rule is working on. That scaling actually follows this set of structure as well. So here's my answer. Our area model. Area follows this structure as well. A 4x3 rectangle is the same area as a 3x4 rectangle. Just turn it 90 degrees. A rectangle with no side length has no area. Okay, it makes sense. Chop up a rectangle to pieces. Add up the areas of the individual pieces. That makes sense. Area manifests itself this way. Here's what I'm saying. To me, multiplication is anything in a scenario that behaves this way. It's defined by its behavior. Not what it is, I have no idea what it actually is, but anything that follows this behavior has the right to be called multiplication. Multiplication is that which behaves this way in whatever context you're talking about. In fraction world, that context is the word of. In counting numbers, that context, that manifestation is repeated addition. In geometry world, that manifestation could be area model, or it could be scaling. In physics or science, when we talk about units, it could be conversion of units. Whatever manifests itself this way deserves to be called multiplication. What it actually is no idea. I just know how it behaves. Here's the amazing thing. That's the power and beauty of mathematics. I've stepped so far away from the practical application. I know there's going to be logical consequences of all this, but I stepped away from it. But I can now look at all these different scenarios. Give me another scenario. As soon as I recognize there's something worthy being called addition in it, and something that behaves this way with respect to addition, then I know that deserves to be called multiplication, and I know all the logical consequences already, and I go, zoom, I can apply everything to that one scenario. That version of addition and multiplication has all these consequences for that scenario, bingo. And in that little world, that's what multiplication is. But in a different world, it's going to have a different meaning, zoom. So here's the beauty of math. You can always look back. The goal is to always look back, step back, and see the uber structure. And don't worry about the practical application. It's not absolute. It just manifests itself in different ways. And that's the beautiful thing, because that then gives you practical application, practical application, practical application, non-practical application, non-practical application, just the beauty for its own sake. It's everything. Math is everything. It's not just the one thing. There is no absolute in maths, other than maybe you want to identify some structure and say, whenever I see that structure appearing, that's what I'm going to call multiplication from now on. Whoa, that is very subtle, very hard. These debates are impossible to engage in because it takes a long time to actually express this point. And I'm not even sure if I did a good job today. Hopefully I've helped to some degree. So I just thought I'd share with the world my thoughts on multiplication. Thanks for listening.